Today we want to start a new unit on magnetism, and as we do that, we have to define a term that's fundamental to the rest of the unit. It's called a magnetic domain. Now, this definition that you see up on the board right now isn't going to make a lot of sense to you if you just read it without any context. It says it's a tiny region. A magnetic domain is a tiny region inside a ferromagnetic material that is represented by arrows. Well, there's a couple of things in here that I think I need to clarify before you really understand what I'm talking about here. One is the word ferromagnetic. A ferromagnetic material is a material that can become magnetized. It isn't necessarily a magnet, but it has the potential to become magnetized. Can you give me an example of a material that can become magnetized? Okay, knives are typically made out of steel. Yes, steel is ferromagnetic, absolutely. Absolutely. You can magnetize a knife, and we know that because when you bring a magnet nearby a knife, that knife is attracted to it, right? You don't necessarily give any kind of lingering magnetic effect on the knife when you just bring another magnet nearby it, but if you can attract that knife, then you can make that knife a magnet. It's ferromagnetic. Another example would be something made out of cobalt or iron. In fact, if you look at the prefix here for ferromagnetic, ferro, where have you seen that before? It's a chemistry, yes, chemistry. What part of chemistry? What's the chemical symbol for iron? Fe. It comes from Latin ferrous or something like that, which means the same thing. Okay? Iron is probably the most common example of a ferromagnetic material. Cobalt is another one. Steel is just an alloy of iron. That's why it's ferromagnetic. Lots of things, though, that you might think are ferromagnetic that aren't. Paper is not ferromagnetic. Okay, paper is not ferromagnetic at all. It doesn't have any domains in it. Copper. You might think copper would be ferromagnetic because it's a metal, but it's not. So ferromagnetic materials tend to be metal things, but not all metal things. Conductors tend to be metal things. Most metals are good conductors, not necessarily good ferromagnetic materials. So a magnetic domain is a tiny little region inside copper, or iron or cobalt or steel, not paper, not copper. Tiny little region inside one of these materials that we represent by arrows. It doesn't mean that when we look at a ferromagnetic material under a microscope that we see a bunch of arrows pointing in whatever direction. We don't. They're not really arrows. It has to do with spins of electrons in these materials and similarities of spins of electrons. We simply represent that by arrows. So, although you wouldn't see arrows if you looked at it under a microscope, we can represent the similarities of spin with arrows. Normally, when we look at a ferromagnetic material, those domains that are representing, or those arrows that are representing the domains, are pointing in pretty much random directions. That's a non-magnetized ferromagnetic material. If, however, we can somehow cause those domains to point in the same direction, or in a similar direction, then we've got a magnet. So this is non-magnetized. Although it is a ferromagnetic material, we know that because it has domains. This is a magnet. This has become magnetized because the domains have become aligned. We'll talk a little bit more in a few minutes about how we might actually accomplish that, how we might make these domains start pointing in the same direction. Domains point in the same direction. It's become magnetized. And we arbitrarily define that direction. It is arbitrary. It could be defined the other way around, but we don't. We arbitrarily define that direction as from south to north. The magnetic domains are pointing away from the South Pole, inside the magnet, toward the North Pole. Now, how do we make those domains become aligned? How do we get them pointing in the direction of being from south, away from the south, toward the north, inside the magnet? How do we get the domains pointing something other than a random direction so that it actually becomes a magnet? Well, there's two ways. The first way is a way that you probably did in grade 4 when you looked at magnetism for the first time. If we have a non-magnetized ferromagnetic material, and we know that we do here because the domains are pointing in pretty much random directions, and we bring another magnet nearby that already has its domains aligned, then these blue domains, these domains that are pointing in the same direction, these domains that indicate an existing magnet with a north pole and a south pole, will cause these black domains, will cause these domains that are pointing randomly to, over a fairly short period of time, start pointing in the same direction. Now, that causes these blue domains that have a distinct polarity associated with them end up causing these black domains that were pointing in random directions that are now pointing in a specific directions to also develop a polarity, a north pole and a south pole. We've just made a magnet. Now, it's temporary. It means it's not going to stick around very long. If I take away this blue magnet, then those domains are going to more or less scramble again and point the way that they were pointing before, more or less. Not going to have its magnetic effect for very long. But at least for a short period of time, I've produced a magnet. I've magnetized this non-magnetized ferromagnetic material, this black material here. Now, of course, if this blue magnet is closer, the effect is magnified. If it stays there for a longer period of time, the effect is magnified. You guys probably tried this in elementary school when you were playing with magnets as well. If you stroke the non-magnetized ferromagnetic material with a magnet, it increases the effect. There's all kinds of things that can increase the effect, but the basic effect is that bring another magnet nearby, align the domains, you got a magnet. Now, the other way, we'll start this because we're not going to talk much about this today. That comes in a couple of days. The other way to align these domains that are more or less pointing in a random direction is to wrap a wire around this non-magnetized ferromagnetic material. Can you see what I've done there? Thanks. Good. Means a lot to me, Jacob. Wrap a wire around it and apply an electric current through it. That's a battery, by the way, the negative terminal of the battery, the positive terminal of the battery. If an electric current goes not through the ferromagnetic material, but through the wire that goes around the ferromagnetic material, and that's going to cause these domains that were more or less pointing in a random direction to start pointing in the same direction. Once again, we've just developed a very specific polarity because the domains are defined as being pointing from south to north. Again, more about the second way in a while here, in another day or two. We're focusing today on the non-electrical part of magnetism. The magnetic fields that are caused by magnets and the domains that are inside magnets and affected by other magnets, rather than the electrical nature of it. Now, we have 3 laws of magnetism, just like we had 3 laws of electricity. I'm going to give you the first one because it's going to kind of give you a hint as to where we're going with this, okay? I'm going to give you the first one, and then you're going to tell me what the other 2 are. The first law of magnetism, similar to the first law of electricity, says that like poles of a magnet will repel each other. That means that north repels north and south repels south. It's not the same thing as saying positive repels positive and negative repels negative. But boy, it sure reminds us a lot of the first law of electricity. What do you think the second one is? Opposite what attracts? Yeah. In the laws of electricity, we said opposite charges attract. Positive attracts negative, negative attracts positive. Now we're going to say opposite poles, or unlike poles, have a magnet attract. So north attracts south, and south will attract north. What about the third law? Third law of electricity, charged objects attract neutral objects. And that happened because of induction, because of a separation of charge that was produced, right? The close side of the neutral object became oppositely charged, which meant it attracted. Charged objects attract neutral objects because of a temporary separation of charge. Now remember, we have something that's analogous to that law with magnetism as well, but don't talk about charges because we're not talking about electricity. Rather than saying charged objects attract neutral objects, what are we going to say? Magnets or magnetized objects attract non-magnetized, one more word, not neutral. We don't want to use the electrical terms in there. Non-magnetized.
Is it the ferromagnet?
Yes, because they don't attract pieces of paper, right? You don't have a magnet attracting a piece of paper, a non-magnetized piece of paper. You have a magnet attracting a non-magnetized ferromagnetic material. The reason that happens, not because of an induced temporary separation of charge, but rather because of a temporary alignment of domains. Now, I could shorten that for you just a little bit because I heard the groans. Both north and south poles of a magnet attract non-magnetized ferromagnetic materials. We could probably safely simplify it by crossing that out and replacing it with the word magnets. Magnets attract non-magnetized ferromagnetic materials. They don't attract paper, they don't attract copper, but magnets will attract non-magnetized pieces of iron or steel. This happens because the magnet causes those domains to temporarily align. Here's my non-magnetized material, domains pointing in random directions. You bring that magnet nearby with a north pole and a south pole. Those blue domains cause these black domains to temporarily align like this, which causes a polarity like this, which causes a force of attraction. So in a similar way that charged objects caused a temporary separation of charge in neutral objects, magnets cause a temporary alignment of domains in non-magnetized objects. In both cases, we get a force of attraction there. All right, let's move forward now and talk about magnetic fields. Yesterday, when we went over our unit test for electricity, we defined an electric field on the very first question as a region in which an electric force could be experienced by a charge. We defined a gravitational force a few weeks ago as a region in which a gravitational force could be experienced by a mass. We defined a magnetic field as a region in which a gravitational force, a region in which an electric force, a region in which a magnetic force could be experienced by a mass, by a charge, by a ferromagnetic material, or by a magnet. So we'll say it's a region in which a magnetic force could be experienced. If there was something there to experience it, it could be experienced by a magnet or a ferromagnetic material. Now, that magnetic field is there no matter what, as long as you have something to cause it, even if there is nothing to experience it. But if there was something there to experience it, there would be a force. Magnetic fields surround magnets. They also surround moving charges or electric currents. We briefly addressed that earlier when we were talking about these two ways to produce a magnet. I'm going to start that again because we'll talk in a lot more detail about that over the coming days. Not so much today. For now, I'm happy if you remember that magnetic fields surround magnets. Think magnetic fields are scalar fields or vector fields? Yeah, they're vector fields. A gravitational field influences masses in a certain direction, and the electric field influences charges in a certain direction, and a magnetic field influences magnets or ferromagnetic materials in a certain direction. So it is going to be a vector field. An example of a scalar field, we talked about this in our last unit, might be a light field or a heat field that influence things, but not in a particular direction. Our vector fields are gravitational, our electric, and our magnetic fields. Here's the first diagram that you should have seen in the activity that you just did. These little stars indicate the points where you want to draw arrows, which in turn indicate the way that a compass needle was pointing when placed at that point. You should get a diagram that looks more or less like I'm about to draw here. Yours might not look exactly like this, but it should look pretty much like this, with the little arrows pointing away from the north and toward the south. How many people got a diagram that looks like this? Pretty much at least like this. Let's start connecting some dots. You can see that the magnetic field lines here, which by the way we represent by the symbol B, with an arrow over top of it indicating it's a vector field. The magnetic fields are pointing away from the north and toward the south. Now remember, the domains inside pointed from south to north. Well, they're really just continuations of the loop of magnetic fields. If magnetic fields go from north to south outside of the magnet, then they're going to go from south to north inside the magnet as they continue that loop. You don't need to draw the next diagram, but I'm going to show you something here that I want to just draw so that we can draw a connection between something that we're doing now and something that we did in our last unit. We have a positive charge and negative charge, and I asked you to draw the electric field surrounding that positive and negative charge. You would draw it looking something like this, away from positive toward the negative. Now that looks an awful lot like the magnetic field surrounding a north pole and a south pole, right? It's not the same thing. The first diagram that we have, the green one, is a magnetic field. The black one is an electric field. Now, by the way, the electric field would point from north, from a positive and negative right here. That's a little bit different than the magnetic field here, right? The magnetic field inside the magnet points from south to north. The difference there is because of the nature of magnetism versus electricity. With electricity, these charges are individuals that we've just put together. With magnetism, you can't have an individual pole. When you have a north pole, you have to have a south pole that goes with it. Okay, does that make sense? So because of that, the nature of the field in between them ends up being a little bit different. Let's take a look at the second diagram now. Second diagram that you saw in your activity looks something like this. The magnetic field lines here would point more or less like this. How many people got something that looked pretty much like this? Yeah? Doesn't have to be perfect, right? Something like that. We start joining the dots here as our little kindergarten activity here. And we end up getting something that looks like, I don't know, kind of like this. These field lines you can see in the middle join up. That shouldn't be a big surprise to us. We learned in our last unit with the electric fields that when you have field lines that join up, it indicates a force of attraction. How do we know that this is a force of attraction here? How do we know that these two magnets should attract each other? Because they're north and south, and we learned earlier that opposite poles attract each other. So when field lines join up, we get an attractive force just like we did with the electric fields. Magnetic fields also produce an attractive force when they join up. Now, again, you don't need to draw the diagram I'm about to draw, but I just want to draw it so that I can illustrate an analogy here. Instead of having a north-south, north-south, I've got a positive, negative, positive, negative. What does the field look like surrounding these four charges? The electric field, that is. Looks like this. Doesn't that look an awful lot like the magnetic field surrounding a north-south, north-south? Yeah, it's not a coincidence. It's always going to look the same. Positive is not north. Negative is not south. But the field lines produced by positive look an awful lot like the field lines produced by north. We get a force of repulsion here, right? Because north is against north. We would expect that because the field lines will not join up. We'll draw our little arrows here. And we should notice when we draw these little arrows that they don't join up. Because if they did, that would indicate a force of attraction. You should have got something that looked pretty much like this. And when you start joining them together, it's going to look something like this. Notice in the middle there, no field lines joining up, which means it's repulsion, which it should be, because north is going to repel north every single time. Now, I don't draw the next diagram there, south against south, but how would it change? If we replace this one with a fourth diagram, north-south, south-north, the diagram would look almost exactly the same with one difference. It's an important difference. Yeah, the field lines would be pointing in the opposite direction. So instead of pointing toward the south, well, it's still pointing toward the south, right? But instead of the field lines going to the left, the field lines would be going to the right in this diagram. All right, let me draw one more electric field diagram to draw the analogy here. You can imagine that I'm going to draw a negative and a positive, and a positive and a negative. You know that the field between these two positives is going to look like this. And then the field between the positive and the negative is going to look like this. Once again, the electric field looking remarkably like the magnetic field surrounding the south-north, north-south. Let's take what we've just done with that activity and use it to define the direction of magnetic field. I'm going to remind you before I uncover the two ways that we define the direction of the magnetic field. I'm going to remind you how we define the direction of the electric field. The first way we defined the direction of the electric field was the way in which a positive particle would experience a force. The direction of the force on a positive particle when placed in the field. You remember the quote, I'm positive the force is with the field. If you're negative, it's opposite to the field, but a positive experiences a force with the field. This is a definition for the direction of magnetic field. It's going to look real similar to that with one important difference. It's not the way that a positive particle would move if placed in the field. Rather, it's the way that we just did it. The way that a blank would move if placed in the field. What is it? No? A compass, yeah. The way that a compass needle would move if placed in the field. Or at least the north tip of a compass needle when placed in the magnetic field. You guys saw that in the activity you just did and the diagrams that we do as a result of that. The magnetic field's always pointed the way that your compass needle pointed. Now, the other way we defined the electric field direction was away from the positive and toward the negative. We're going to define the direction of magnetic field in the second way as well. Away from the north and toward the south. Yeah, that is, as long as we're outside the magnet. Outside of the magnet. Inside the magnet, it's actually the other way around. But 9 times out of 10, whenever we're dealing with magnetic field, we're dealing with the magnetic field outside of the magnet, not inside. So remember that inside it is opposite, but most times we're dealing with outside, so it's going to be from north to south. This page is just designed to provide us with a little reference as to what various strengths of magnetic fields can be. We're just comparing the Earth's magnetic field strength to human-made magnetic field strength, bar magnets, magnetic neutron stars, so on. The Earth's magnetic field is, on average, it varies, in some cases quite dramatically, depending upon where you are on Earth, but on average, it's about 10 to the minus 5 Tesla. That's a weak magnetic field. Does vary quite dramatically, and in fact, over the last several decades, the Earth's magnetic field has decreased somewhere in the range of 10%. So much so that, in fact, there's some scientists that believe, like mainstream scientists, that believe we're actually in the process of a magnetic field reversal. So north will become south and south will become north. We don't know that, but geologic records show that about every 250,000 years, the Earth's magnetic field will reverse. And the last time it happened was about 750,000 years ago, meaning that we're about 500,000 years overdue for it happening. Because we're 500,000 years overdue, and because the Earth's magnetic field has decreased dramatically over the past few decades, again, some scientists think that that's the beginning of another reversal. Now, if it does reverse, it's not going to happen by tomorrow, but it's also not going to take another 10,000 years. Okay, maybe another 100 years, and the Earth's magnetic field will reverse. It's entirely possible, I wouldn't even necessarily say probable, but entirely possible that your children or grandchildren will have a magnetic field that's opposite to the magnetic field that we have today. In other words, when we go north, we'd really be going magnetically south. And when we go south, we'd be going magnetically north. Yeah, question?
So in like the middle of it, like transitioning,
Yep.
compasses just like stop working.
Well, if the magnetic field strength was actually 0 at some point, then yes, compasses would stop working. Now, I don't know if that would happen. I don't know if we'd ever reach a magnetic field strength of 0 or whether it would decrease and then flip. Okay, I'm not sure that anybody really knows the answer to that question because none of us were alive the last time that happened. But yes, if the magnetic field was 0, compasses would stop working. And it would affect a whole lot of things, including we get solar activity, charged particles coming from the sun, solar wind we call it. Okay, charged particles coming from the sun all the time. The Earth's atmosphere does a decent job of filtering out those charged particles coming from the sun, but the Earth's magnetic field also plays a big role in deflecting those charged particles coming from the sun. That would have some pretty serious implications for us and for our health, but it would also have some serious implications for things like communication satellites and so on. All kinds of things would be affected by a dramatically weakening magnetic field, and even more so by a completely absent magnetic field. A bar magnet, on the other hand, has an average magnetic field strength of about 10 to the minus 2 Tesla, about 1,000 times the Earth's magnetic field. Again, it varies, obviously, depending upon the bar magnet, but on average, about 1,000 times stronger. That shouldn't be a surprise to you. When you did the activity a little while ago, you had a bar magnet in the center of your desk. When you placed a compass nearby that bar magnet, the compass wasn't affected by Earth nearly as much as it was affected by the bar magnet. That indicates that the bar magnet is stronger than the Earth's magnetic field. On average, about 1,000 times stronger. Sunspots, charged particles released from the sun, generate a magnetic field that's about 10 to the minus 1 Tesla. So about 10 times the strength of a bar magnet. Anybody had an MRI? Anybody ever had an MRI? Yes? When you get an MRI, they give you this like 2 or 3 page questionnaire that asks you all kinds of crazy questions. For instance, one of them, I remember one time I had an MRI years ago. It asked me about ever having pieces of metal embedded in my eye. No, I've never had pieces of metal embedded in my eye. But why would they ask me that question?
Just in case you have metal embedded in your eye.
Well, specifically, a specific type of metal embedded in your eye, right? If it's copper, it doesn't really matter in an MRI machine. If it's ferromagnetic metal, like steel, then it could potentially matter with a magnetic field strength of about 15 Tesla, 10 to the 1 Tesla. Now, I don't know what they'd do if you answered yes to that question, whether they'd not give you the MRI or whether they would. I don't know. I don't know what effect that would have, but I assume that's why they asked that question. The strongest human magnet ever? Well, when I made this notes up, it was 40 Tesla. I read about a month ago that a lab, and I want to say it was in Japan, I'm not positive about that, built a human magnet that was dramatically stronger than 40 Tesla. You can Google this. It literally blew up the lab. Their lab literally blew up as a result of the massive amount of electric current that it required in order to generate this magnet. But they set a world record. They made the strongest magnet ever. Finally, a magnetic neutron star. This is what you want to stay away from. That's about 10 to the 11 Tesla. I would assume, I don't know this for sure because I've never been close to one of these things, but I would assume if you ever did get close to one of these things, that would be a strong enough magnetic field to probably suck the iron right out of your blood. The good news is, you're not likely to ever be close enough to a magnetic neutron star that you're going to have to worry about it. If you do, the iron getting sucked out of your blood is probably about the least of your concerns. Now, you don't need to memorize these numbers. The reason I give them to you is A, for perspective, and B, when you're solving a problem later in the unit and you solve for a magnetic field, we always want to see if our answer is reasonable. If you get a magnetic field strength in a question that's 10 to the minus 23 Tesla, that's not reasonable. That means you're probably wrong. If you get one that's 10 to the positive 17, again, not reasonable, probably wrong. If you get one that's 10 to the minus 3, that seems much more reasonable, right? At least now we have not necessarily specific numbers that we have to remember, but a range that maybe we want to be in. Somewhere 10 to the minus 5, 10 to the minus 6, up to about 10 to the 1 or so. If you fall within that range, there's a good chance that you've answered the question correctly. One more thing. We'll finish off the day on this. Nobody's called me on this yet. I'm surprised a little bit. We defined the direction of the magnetic field in two ways. The way in which a compass needle would point and away from the north toward the south. The Earth contains a magnetic field. And the magnetic field surrounding the Earth looks like the magnetic field surrounding a bar magnet. Clearly, there's not a bar magnet inside the Earth. There's a magnetic field that's somehow, we're not exactly sure, but somehow it's caused by churning magma within the Earth. Somehow. We're not exactly sure exactly the mechanism for that, but we know that there is one produced somehow by the churning magma within the Earth, and it generates a self-sustaining magnetic field. And that magnetic field looks like this, very much like the magnetic field surrounding a bar magnet. So we pretend there's a bar magnet inside the Earth, even though clearly there isn't. This is the equator. If I was to stand at the equator with a compass, which way would that compass needle point? Keeping in mind, this is Canada, and this is Antarctica. Which way would the compass needle point? Yeah, up towards northern Canada, right? Same deal over here, right? But remember, the other way we define the direction of the magnetic field. We define magnetic field as being the way that a compass needle points, and we define it as being away from the north and toward the south. So what are we really saying here? Geographically, Canada is north. Magnetically, Canada is south. Geographically, Antarctica is south, but magnetically, Antarctica is north. At least for the time being, for the next couple hundred years at least, maybe the next couple 100,000 years for all we know. Canada is magnetically south, and Antarctica is magnetically north. Now, if you ever wondered why, when you were 4 years old, and you asked Santa Claus for that cool Pokemon toy, and you never got it, now maybe you understand a little bit more. Because when you were 4 years old, and you sent that letter to Santa Claus, you sent it to Santa Claus in the North Pole. But where does Santa Claus really live? Everybody knows now that Santa Claus lives in the South Pole. And the penguins, they don't live in the South Pole. The penguins live in the North Pole, magnetically. Does this change the way we navigate? Of course not. Okay, everybody calls, when you're navigating, everybody calls this the North Pole. It's not. Magnetically, it's not. It's the South Pole. But if we all call it the same thing, if we're all using the same frame of reference, doesn't really matter. It's called magnetic south. We all call it north. But even if we called it Bob, if everybody called it Bob, and Austin said, which way is Edmonton? And Jacob said, oh, head Bob. Well, then Austin would know exactly what Jacob was talking about, right? It's just a word. Okay? Magnetically, it is south, the way we define the direction of the magnetic field. But really, when it comes down to it, it is just a word.